Hi everyone. Now that we have got an understanding of Android features, its applications, various API levels, and Android ID, let me tell you about its architecture and OWASP Mobile Top 10 security vulnerabilities. Now there are four layers of Android architecture. The first layer being the Linux kernel, then comes native layer, which is divided into two parts, libraries and Android runtime, application framework, and application layer. Here is a diagrammatic view of how the layers are distributed in Android architecture. The bottommost or the first layer being the Linux kernel, then comes a native layer which is divided into two parts, then comes application framework and then the applications. Now Linux kernel. It is the first layer of the Android architecture. It is responsible for handling all the hardware drivers including camera, Wi-Fi, Bluetooth and so on. It efficiently handles memory management, allocates resources to processes whenever needed, and ensures that hardware manufacturers can build their drivers into the Linux build. The second layer of Android architecture is a native layer, which consists of libraries and Android runtime written in C and C++ native code. The first part of the native layer is the libraries. Some of the key main libraries includes OpenGL, SQLite, WebKit, SSL, and Media Framework. OpenGL is responsible for producing 2D and 3D graphics. Media Framework is for playing and recording audio and video. WebKit for providing web browser functionalities. SSL for internet connections and SQLite for storage and database. The second part of native layer is Android runtime, which includes core libraries and Dalvik virtual machine. Core libraries enables Android application developers to write applications using Java. Dalvik Virtual Machine or DVM is like Java Virtual Machine, but it is optimized for mobile devices. It consumes less memory and provides fast performance. The third layer of Android architecture is the application framework. It is a key set of services that collectively form the environment in which Android applications run and are managed. Some of the key services of Android framework includes Activity Manager, which controls the activity lifecycle of all apps, content providers, which allows applications to publish and share data with other applications, Notification Manager, and several more. Then comes applications. It is a top layer of Android architecture consisting of all the Android applications like home, contacts, phone, browser, games, and so on. Now comes Dalvik Virtual Machine. We can understand Dalvik Virtual Machines working in this diagrammatic fashion. Dalvik Virtual Machine, is, as I told, is an optimized version of JVM used for Android devices. It has excellent memory management and optimized battery features. In DVM, first a Java source file is compiled into .class file using the Java C tool. The .class file is further converted into .text file using the DX tool. The Android Asset Packaging Tool (AAPT) handles the packaging process of Android and creates .apk file. Now we come to OWASP Mobile Security Top 10 Vulnerabilities. OWASP Mobile Security Project is a centralized resource that intends to give developers and security teams resources to build and secure mobile applications. They have classified the security risk into top 10 based on the impact and risk of exploitation. The top 10 mobile security risk according to a latest OWASP top 10 list includes improper platform usage, insecure data storage, insecure authentication, insecure communication, insufficient cryptography, insecure authorization, client code quality, code tampering, reverse engineering, and extraneous functionality. Now let's discuss the first OWASP Mobile security vulnerability, which is improper platform usage. It covers misuse of a platform failure or feature to use platform security controls. It might include Android intents, platform permissions, misuse of Touch ID, the keychain, or some other security controls that is part of mobile operating system. There are several ways of mobile apps that can experience this risk. Some of the ways include violation of published guidelines, violation of convention or common practice, and unintentional misuse. It can be secured using best coding practices and configuration practices on the server side of mobile apps. Next we come to insecure data storage. It covers insecure data storage and unintended data leakage. It is made from the combination of the M2 and M4 in OWASP Mobile Top-10 in 2004. It occurs when development teams assume that users will not have access to phone mobile file systems and store sensitive pieces of information in data stores on the phone. Devices file systems are often easily accessible, and you should expect a malicious user to be inspecting your data stores. Now comes insecure communication. It covers poor handshaking, incorrect SL versions, weak negotiations, and clear text communication of sensitive assets, and so on. Risks of insecure communication includes loss of data integrity, confidentiality, and origin. Now we come to insecure authentication. This category captures notion of authenticating the end user or bad session management. It can include failure to identify the user at all when it is required, failing to maintain user's identity when it is required, and weakness in session management. One attack scenario includes fake or bypass authentication by submitting service requests to mobile app's backend server and bypass any direct interaction with the app done using mobile malware or botnets owned by the attacker. Insufficient cryptography. This code applies to a sensitive information asset. However, the cryptography is insufficient in some way. To note, everything related to SL or TLS goes to insecure communication, and if the application fails to use cryptography, that goes under insecure data storage. This category is for issues where cryptography was attempted but it wasn't done correctly. Some attack scenarios include decryption of data via physical access to device or network capture. Insecure authorization. It relates to any failures in authorization, for example, authorization decisions in the client side, forced browsing, and so on. It is distinct from authentication issues, for example, device enrollment, user identification, etc. It can be bypassed using IDOR or insecure direct object reference vulnerabilities, hidden endpoint vulnerabilities, or user role permission vulnerabilities. Client code quality. This was a security decision via untrusted inputs, one of our lesser categories. This would be the catch for all for code level implementation problems in the mobile client. That's distinct from server side coding mistakes. This would capture things like buffer overflows, format string vulnerabilities, and various other code level mistakes where the solution is to rewrite some code running on the mobile. It can lead to high critical vulnerabilities such as buffer overflow attacks. Now, code tampering. This category covers binary patching, local resource modification, method hooking, method swizzling, and dynamic memory modification. Flaws in code tampering can allow attackers to make direct binary changes to apps package, its resources, and redirect or replace systems APIs. Now we come to reverse engineering. This category includes analysis of final code binaries to determine its source code, libraries, algorithms, and other assets. Software such as IDA Pro, Hopper, OTool, and other binary inspection tools gives the attacker insight into the inner workings of the application. Now, exploiting this technique or reverse engineering can reveal information about backend servers, cryptographic ciphers, and constants. Now, extraneous functionality. Often developers hide inner hidden backdoor functionality or internal security controls that are not intended to be released in a production environment. Here there was no authentication like password, hence anyone could connect to device and get full access. Thank you and stay tuned for the upcoming videos.